Welcome, VinniPhysics here. This is video 3 of 3, analysis of the Mythbusters episode, Fire Bullet versus Drop Bullet. In video number 2, I showed that my projectile model with air resistance predicted a 7 millisecond difference between a drop bullet and a fire bullet. The Mythbusters experiment showed a 39 millisecond time difference. The Mythbusters seemed to be satisfied that the 39 millisecond difference was close enough to 0 to assume that it was 0. And let you watch that part of the episode, and we'll come back and talk some more.
Physics. Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film is made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
2 bullets, 1 dropped, 1 fired. Amazingly, they ended up in the same place at the same time.
Okay, so again, clearly a 39 millisecond difference based on their measurements, but it seems like Jamie wants to conclude that let's just go ahead and assume that's 0. Same place at the same time. So did the Mythbusters get it right? No, in my opinion. Based on physics theory and a widely accepted projectile motion model with air resistance, there should be a time difference between a drop bullet and a fire bullet. Their experiment, I think, was good. Very difficult experiment to carry out, but they showed a 39 millisecond difference. Their equipment had the ability to measure time differences as little as 2 milliseconds. What I was curious about was why I got 7 millisecond difference and they got 39 millisecond difference. Again, there should be a time difference. So I tried different drag coefficients in my model, a wide range of drag coefficients, and I never got more than a 10 millisecond time difference between the fired bullet and the drop bullet. It's possible they didn't get their gun to fire level, and I'm going to go back and take a look at their fired level test. Third possibility is the bullet they fired had some lift. Normally, we wouldn't expect a bullet, because it is symmetric about the rotation axis, an axis right through the center of it, a longitudinal axis. Because of that symmetry, we wouldn't expect there to be lift. But maybe the bullet had flaws. So there's a possibility the bullet may have had some lift. My model assumes no lift. So let's go back and look at 3313 of the video, the fired level test.
So with the gun rest in place at one end of the room, Adam's first job is to make sure it's exactly 36 inches off the floor. And firing level.
I'm going to fire a bullet to that target 20 feet away. Now within that 20 feet, the bullet's not going to drop at all. So as long as the bullet hole in that target is the exact same height off the ground as the barrel, I know I've got a perfectly level bullet.
Seating the gun rest. Firing in 3, 2, 1.
Dude, I'd say that is absolutely perfect. Right on our laser line. That gun's firing level.
Works for me.
Okay, definitely a flaw in that analysis. Adam said that over the 20 feet where their test ribbon was, the bullet wouldn't fall at all. But we know that as long as the bullet's in the air, it's going to be falling at 9.8 meters per second squared. So if he did indeed measure that 20 feet away, the bullet was still 3 feet off the ground, that means it must have been fired at an angle above this horizontal. And I estimated this angle to be 0.02632658 degrees. So how did I come up with that? Here's my equation for the y-coordinate of the bullet at any time t, given a launch velocity here and a launch angle here. So I took that equation, I set my coordinate system, the origin of my coordinate system here. So this is the x direction and the y direction. And I'm interested in the time it will take to go from initial height of 0, again, I'll put my origin here, back again to 0. So that's what I've done here. Taking this equation, 0, 0, the launch velocity, 255 meters per second. Acceleration due to gravity, it's 1/2 of that, 4.9. I divided both sides of this equation by t, and I'm left with this. So I only have one t here. So I've solved for this equation, the time for which it launches here and ends up here in the vertical. And I plug that into this equation here. I set my x-coordinate to 20 feet away. I've converted to meters here. And I'm going to solve for the launch angle. And I got 0.02632658 degrees. So at that angle, 20 feet from the launch, I would expect the bullet to be back here, satisfying Adams' test, that it was 20 feet here. Again, he made the assumption that the bullet wouldn't drop over that 20 feet. Maybe he meant that it wouldn't drop much, or an immaterial amount. But is he right? Is it an immaterial amount? Is it an immaterial angle? If we launch this bullet at 0.02632658 degrees to the horizontal, how much of a difference will that make in the time it takes to hit the ground? So I plugged that into my model, and it actually made quite a bit of difference. I went from 7 milliseconds to 18 milliseconds. Obviously, if you launch at an angle, it's going to take a little bit longer to hit the ground. So that's quite a bit. That's 17 milliseconds explained by possibly not getting that fire level test right. So I'm closer now to the 39 milliseconds they got, assuming this is the error they made, but not quite the 39. And again, the only other thing I could think of was possibly the bullet was flawed and there was actually a bit of lift. So, conclusion. Scientific method, right? You have a theory, you have a hypothesis, and the experiment doesn't tie to the theory. They got a 39 millisecond difference. If you do have a difference, you got to explain that away. To the limit your technology can do so. And they had technology that could enable them to tell a difference of 2 milliseconds. And as I was watching this, I was remembering a famous experiment done, or a famous discovery made by Penzias and Wilson. They were working on a project for Bell Labs, and they discovered noise coming to them from all different directions, and they couldn't explain it. And when word got out that they had discovered this, researchers at Princeton called them and said, listen, I think what you discovered is the radiation from the Big Bang. But what these guys did is they didn't walk away from it. They tried to explain it by doing all sorts of control tests, and they couldn't explain it. And so they said, something's up here, okay? And I think that's what the Mythbusters should have done. 39 millisecond difference. What's going on? Why is there a difference? Where is the... maybe we've discovered some new physics. I don't think that's the case. I think it's in the experimental method, or again, maybe the bullet was flawed, whatever. Okay, again, the physics theory said there should be a difference. Anyway, great episode. Extraordinary work on their part, developing the apparatus. Okay, the other thing I promised in the last video was a little bit about the model which I built to estimate the time for a bullet fired to hit the ground and the time for a bullet dropped to hit the ground. This is a well-known model, projectile motion model with air resistance. And this is what I did. So the force I'm interested in modeling here is gravity, but also the drag force. And it's 1/2 times the drag coefficient times air density times the cross-section area of the bullet. And that's the area perpendicular to the velocity vector of the bullet. I set my time step at 0.001 seconds. You want to set this as small as possible. So my initial conditions are x is 0, y is 0.91463 meters. Here are my initial velocities, 262 meters per second in the x direction, 0 in the y direction. So the first thing I do is I compute the acceleration in both the x and y directions. In the x direction, it's just the drag force. Here's my velocity, it's the x component squared plus the y component squared square root. Here's the velocity in the x direction. In the previous slide, I was modeling this as v cosine of the angle to the horizontal, which is changing. It's the same thing. The y acceleration is gravity down and drag force in the opposite direction. And then I compute the deltas. So the change of the velocity in the x direction is the acceleration in the x direction times this time step. Same for the velocity in the y direction, except I'm multiplying the time step by the acceleration in the y direction here. Then I'm updating my velocities. The previous velocity in the x direction plus the change over that time step. Same for the y direction. Then I compute the change in the x coordinate by multiplying the velocity in the x direction times the delta t. Same for the y. And then I update my x coordinate by taking the previous x coordinate and adding this value. Same for the y. And I continue this loop until the thing is on the ground, y is equal to 0. I also I entered a command in Mathematica using NDSolve, and I got about the same result. Okay, so the other thing I mentioned in video 1 is that a projectile will follow a parabolic path. And I think what I stated was a fired bullet would follow this path, right? Okay, so what I've got here is something that actually has a launch velocity in both the y and x direction. For the bullet, it only had a launch velocity in the horizontal direction. But this could apply to any projectile. I'm using the mathematics associated with a projectile without air. So we launch, let's say we kick a football, and the launch velocity off the person's foot is v sub 0, and the launch angle is Greek symbol theta. Okay, so this would be the x component of that velocity, and this would be the y component. Okay, so the position of the ball, right? The position of the ball, the x-coordinate position, is the launch velocity times the cosine of the launch angle times the time. The time into the path of the projectile. Say maybe 1 second after launch, right? 2 seconds after launch. 3 seconds after launch, it's on the top. Here's the y-coordinate equation. It's the launch velocity times the time minus 1/2 the acceleration due to gravity times time squared. So what I do here is I solve this equation for t, and I plug that in here for t, and I end up with this equation here. Okay, and that is what I anticipated, or what I projected in video 1, that the path of a projectile is that of a parabola, and that's an equation for a parabola. Constant times x plus a constant times x squared is the y-coordinate. Okay, this is a constant. Tangent of the launch angle. This is also a constant. This is my constant 2. Okay, so there you have it. So that about wraps it up for the Mythbusters episode, bullet fired versus bullet dropped. I hope this was helpful to you, and appreciate you watching. Have a good day. Bye-bye.
Thank you.